So a couple of very useful features I like to use on my graphing calculator are second answer and second entry. Going back to this half-life problem I was doing earlier, I did the calculation log of 7 divided by 32 divided by log of 2, and I actually just realized I did 8 instead of 7. So rather than retype this entire thing, I can just do second entry, and it pulls up the last operation I did. So I can just change that 8 with the 7. And this is so useful because if you're doing very longer computations or dealing with bigger numbers, it saves so much time to just do second entry rather than typing in the entire thing again. And now the last part of the question was dividing by this. And instead of typing this entire thing, I'm going to do second answer. And this is nice because, again, it saves time from retyping this entire thing. And additionally, it won't. It's this. This isn't round. This is not rounding. So I'm not really rounding until like the very end. So I use the second answer and second entry features all the time. Another feature that I find very useful is the second calc features for when you're dealing with graphs, especially at college algebra. You know, when you're dealing with max and mins or have to find zeros. It's so powerful if you know how to use these features. The next thing I wanted to talk about was arithmetic and conventions. So I am going to start by writing the following system of equations: 2x plus 2y equals 4, and 3x minus 3y equals 6. So one of the first things I wanted to talk about was I don't like dealing with negative numbers. And I know that may sound a little bit vague, but I'll show you what I mean with this problem. So a lot of students, when they see this, they'd be inclined to manipulate this first equation. They might say that y is equal to negative x plus 2. And then they would proceed to plugging this into that. And that's totally valid, but I would actually approach this a little bit differently. Instead, I would manipulate the bottom equation. I would solve for x. In this case, x would be equal to y plus 1. And the reason why I did that is because when I plug this back into the first equation, after I distribute and combine, after I plug it in, everything's positive. Whereas if the student plugs this into this equation, they take a risk. The student takes a risk of distributing this negative, and especially if the student's tight during a knowledge check or something, it's very easy to forget to distribute a negative or change the sign. And my point is you increase your likelihood of making mistakes if you're dealing with that negative. So as another example, I'm going to write the inequality 4 minus 2x is less than or equal to 6 minus 2y. So the question would be something like, maybe graph this inequality. And naturally you'd want to solve for y. So a lot of students, might say, oh, well, let's just subtract 6 and then we'll divide everything by negative 2. And that's totally fine. My problem with that is if you divide everything by this negative 2, you're going to have to flip this inequality sign. So what I would do instead is I'd move this to that side and then this to that side. So I would have 4 plus 2y is less than or equal to 6 plus 2x. Now, by solving for y, so I believe that'll just be 1 plus x. By doing it this way, everything's positive. I didn't have to flip the sign. And again, when you introduce more possibility of making a mistake when you're dividing by this negative, because you might forget to flip this. And as I said earlier, when you're under pressure doing the exam, it's so easy to overlook that. So if possible, at least like in these problems, always try to keep everything positive if you can. And if you do have to do negative, well, then so be it. But in these kinds of cases, I would choose the positive if you can. So the next thing I wanted to talk about are solving word problems. And there's kind of 4 general guidelines to doing the word problems that I found useful. So setting the problem up, pictures, units, and then checking your actual answer if it's practical. So a problem I was working on with a Math 100 student recently was how many turns does a log make rolling down the ramp? And this student was pretty puzzled. The student didn't even know where to start. And I just showed them a picture because they didn't understand, I think, like turns and how a log makes a turn. So basically, I just drew a ramp and then a log rolling down the ramp. And this may not seem like that much, but it's pretty amazing, like just how illustrative the picture can be. And once I was able to draw this, then they were like, oh, I see. So I need to find out how many times it turns. And so drawing the picture is very, very useful. And as far as setting up the equation, setting up the actual problem, so then they would proceed to like number of turns would be equal to the length of the ramp length divided by the circumference. I'm not actually going to solve for this, but just because once they were able to figure out the setup, I mean, it's just a matter of plugging in numbers. And I emphasize the setup because I find the tendency, it's the word problems, the actual math isn't usually too bad. It's just setting the problem up. And to really illustrate just how important setting up is, one of the midterm review problems I was looking at last month, I think. So these problems I find kind of annoy students a lot. It's like a quadratic or polynomial problem because they give you so much different information. And this also kind of brings up the other things I was talking about earlier. So I'll probably talk about a little bit more about units and answers. So in this problem, what's tricky about this is that, again, the math is not too bad. It's really just setting this thing up. And it's hard to set up because they give you so much information. So my suggestion to the students was match units together. So in this case, y would equal, so dollars to dollars and then tickets to tickets. So 9.50, 9.5 plus, so 0.1x times 600 minus, so 6 fewer, that means 6 less than x. And I cannot tell you how many times I've seen students do like 9.5 plus 6x or minus xx, or like 600 plus or minus like 0.1x. And the way you get that sorted out is by units. Dollars and then number of tickets. So one of the reasons why I like this problem too is because this is a good test on how skillful you are with your graphing calculator skills, because you do have a couple ways you can go about this question. You can use your graphing calculator, or you can do this algebraically. So I'm going to go straight to my graphing calculator. 9.5 plus 0.1 x times 600 minus x. Oh, sorry, minus 6x. So, and again, they may get a little fearful, like I don't see anything. Well, going back to the zoom features I was doing earlier, I'm going to fit it. So almost the entire thing. So I'm just going to zoom out just once. And then after using my zoom features, now I'm just going to use second calc to find the maximum, the value of the maximum. So x equals 2.5, and then y equals 5701. And this is kind of cool because it really does set me up to solve the entire problem. The price that should be charged for each ticket. So when x equals 2.5, so you have to keep in mind that's the number of tickets. So x is the number of tickets, so we would just plug that back into this first equation. And if we plug in 2.5, that would be 9.5 plus 0.25. So that would be like 975 or something. And this is pretty cool because we actually found our second answer now. Find the maximum possible revenue. Well, that's just the y value of our max, and it's 5703, which is clearly less than 5800. Now, so I think I was able to do that problem with pretty good time, but that's only because I was able to use my graphing calculator well. Now, if you can't even get this, if you don't know the zoom features, you're going to have to play around with the window. And as I mentioned in one of the previous videos, adjusting the window can be a very tedious task. Whereas the zoom features, I only had to do 2 steps. And additionally, I talked about how you could do this algebraically. So and you can do this algebraically, but it's going to require a little bit more labor, I'll say, because now you have to FOIL this entire thing out, and then you would have to proceed with something like doing x equals like negative b over 2a to find the vertex, and then, or that'd be the x value of the vertex. Then you'd have to plug that back in, and you'd still get your 9.75. But in order to get the maximum possible revenue, you'd have to plug this x value back into this entire equation, and that's just going to eat up a lot of time plugging stuff into your calculator. So the keys to doing this word problem was the setup, which I got from doing the units. And I also want to just mention that when I was talking about having like practical answers, when I say that, I don't get anything like negative money or negative time. So those are examples of practical and impractical answers, but these are the general guidelines I like to use for the word problems, and once you can get a habit of doing these guidelines, they're not too bad.